Welcome, everybody, to the Into the Impossible podcast, a production of the Arthur C. Clarke Center for Human Imagination at UC San Diego. And we are named after one of Sir Arthur C. Clarke's famous three laws, the first one being for any expert, there's an equal and opposite expert. The second one being any sufficiently advanced technology is indistinguishable from magic. And the third one being the only way to find out what is possible is to venture beyond a bit into the impossible. So Sabine, that's where we get it. I think you exemplify many of those different laws of, you're an expert. Oftentimes you're oppositional to other experts and putting them in their rightful places. You work on advanced technology in the form of higher mathematics and physics. And you've done the impossible because you've actually communicated science to a whole generation of people at a very technical level, but not dumbing down anything you do. And I have so much respect for your book, which is coming out in paperback. So first, I want to welcome you, Dr. Sabine Hossenfelder, from joining us all the way from Germany right now, where it's late in the evening. Thank you so much for joining us on the podcast, Sabine.
Thank you in return. And it's good to see you, Brian.
Yeah, it's good to see you too. I was looking back because I was going to email you. We've been communicating via Twitter direct messages, which is probably the least effective form of communication, but it works. It works okay. And then I looked back. I gotta have her email somewhere, and I looked up, and there was an email invitation that you had sent me for a conference in 2009, which I think was at Nordita that took place. Maybe It was 2010. And that was actually when we found out about it. When we went there, I took my wife, and we found out, kind of along the way, that we were pregnant with our first child 9 years ago. And I suspect that you were pregnant also with your first and second child, right?
Yeah, that's right.
So
that was a legendary conference.
That was great. I love that conference, except for the accommodations. It was the hottest time ever.
Oh, yeah. Stockholm. Oh, my God. I remember this. It was so terrible. I was so sorry about it.
Yeah, but it was nice because it actually got me, my first exposure to the enthralling world of Nobel Prizes and so forth, and even took a detour over there. I want to point out I tweeted about this today that you're my fifth guest, and if you include me, I've been a guest on my own podcast, I suppose. 6 guests out of 50 episodes have twins. It's pretty remarkable. So I'm very proud of that. And of course, we realized that in in relativity theory, Einstein was guided by these Gedanken experiments, these so-called thought experiments. And he was a theorist, but he dabbled in experiment. And much of what I think interests me about your work is to see how a theorist looks at things, but with an eye towards what can we prove and what can we say about things. So first of all, I want to talk about your wonderful book, Lost in Math, which came out 2 years ago in hardcover and is coming out next week in paperback. Can you talk a little bit about that book, what led you to write it? Because it's not an ordinary popular science book with whiz-bang wormholes, and it's almost, not only is it almost the opposite of that, but it's a memoir, and I call it the heroine's journey, where you kind of make this travel log across the world. Can you talk about what motivated you to write it and what it was like writing that book?
So the book is about me trying to make sense of what is going on in the foundations of physics, where we have all these people looking for, theory of everything, grand unified theories, trying to reinvent the foundations of quantum mechanics. And at some point, I just couldn't understand anymore why they are doing what they are doing. And so that's when I set out on this journey, which I write about in the book. So I talk to people in the field and ask them, what's going on? What do you think you're doing? Please explain it to me. And I try to communicate this to the reader, it was quite some challenge because, so with the exception, I think, of Steven Weinberg, everyone who I talked to knew that I'm a physicist. So even though I told them, please don't be too technical because I won't be able to put this in a book, they would start immediately talking about the details. And so then I had to try to explain this in the book. so it was quite difficult to make this work. But in the end, I think it worked out fine. So you have these interviews with me in between explaining what's going on, and I made a lot of effort to put it in the right order so there would be no gaps. Yeah, so it's basically a portrait of what's going on in the foundations of physics. And towards the end of the book, I try to put this into the broader context of the general problems that we have with, in other scientific disciplines, all the trouble that can happen from the pressure that a lot of people are under, financial pressure, time pressure, the pressure to publish, the pressure to get something done within the constraints of a little grant that you have. And it's not working very well, I think. And so in the foundations of physics, I think it's particularly pronounced because we have this detachment from experimental checks, and many of the questions that we're trying to answer are just so hard. You basically can't get anywhere within 2 or 3 years.
And when I read the book, it speaks to me. First of all, I learned a lot from it. Not only what your perspective is a unique one in that the attraction to beauty and to symmetry and all sorts of things are leading scientists to really forget what is unique about science, and that it isn't art. And I kept thinking as I'm reading it, have you ever seen these pictures where they take like Brad Pitt, who's the handsomest man in the world, according to the reputable science journal called People magazine here in America, or OK. And they take his face and they split it in half, and then they mirror reflect one half onto the other. So it's perfectly symmetrical, at least, parity symmetrical. And he looks grotesque. And, this is the most attractive man in the world. So it started making me think that, is it really true that great beauty is truly symmetric, or is it just a cop-out, or is it just a shortcut, a mental hack to use symmetry to avoid doing things? In other words, is physics actually more symmetric than even art is?
Well, symmetry is not the only kind of beauty, of course. So I think the reason even the supposedly most beautiful man looks terrible if you do that kind of thing is that we realize immediately it's unnatural. So it just freaks us out, right? So this is not a real human being. I think that's where it comes from psychologically. But I mean, it is well established that our sense for symmetry very, very likely has an evolutionary origin. We like things that are symmetrical because in many instances, symmetry is a sign of health. So it makes sense that we like it, but does it make any sense that we expect nature on the most fundamental level to appeal to this very sense of beauty that we take from apples, basically, right? And so this is what leaves me perplexed, that scientists don't question this. Like, why am I using this criterion? Why do I rely so much on this sense of beauty if there is no reason to think that it actually tells me something about what I'm trying to achieve? In this case, trying to understand, I don't know, the quantum nature of space and time or something like that. So in the foundations of physics, we have this very peculiar problem that arguments from beauty have become very commonplace, and very few people question it. It's just because everyone is doing it, it seems to have become okay.
Yeah, and I wonder, if I'm trying to show a picture of me with someone named Max Tegmark at MIT when we.
Okay, but it's cut, without the heads.
Yeah, no heads. So they're, he's extremely attractive, even when you cut off his head, apparently. So I'll switch back to your cover. So we talk about physicists and especially theoreticians. I have yet to really see an experimentalist focus on beauty as a criterion, although I do want to get into that for a bit, because, and you and I met again about a year and a half ago in Los Angeles talking about your book in front of other, basically all theoretical physicists except for me are mathematicians, including Eric Weinstein, Stefan Alexander, and Priya Naratajan and others. And the question was, what is it about the topics and the kind of issues raised, and at least what I call the polemical. Your book is really divided in at least two parts. One is a polemic about this very issue and the perniciousness that it may prove to be for physics and progress in the 21st century. But it's also this travel log and this, heroine's journey around the planet, literally. And there's so many delightful scenes in there. But I tried to make the point in that gathering of, brainiacs that, beauty is essential, or, to an experiment. Like there are experiments which aren't beautiful, but experiment, like the transistor, if you've ever seen the first transistor, it's a piece of chewing gum over here, a crystal there, and a coat hanger there, and it magically works. So, I mean, it's beautiful judged by its results. But for example, we just put out a paper on the polar bear team, which I'm a part of, which is a cosmic microwave background polarization experiment, who has an ultimate goal to measure and constrain the existence or lack thereof of primordial perturbations in the metric of space-time, potentially caused by gravitational waves, potentially the byproduct of inflation, which is potentially a harbinger of the multiverse. So you have all these different chains, and we'll get into each one of those. And I know your feelings are very well known on those, but I want to recapitulate them to the audience. So now I have this experiment, and along the way, we spent 6 months, or the graduate student working on this, to be precise, and her advisors, they spent 6 to 9 months looking for departures from symmetry. In other words, we're doing null tests. We're trying to torture the data in as many ways as possible that should yield a zero signal. And yet, every time we do that, we find there are some departures for that. And that's a form of symmetry. Would you agree?
Sure, there are many forms of symmetry. So let me maybe be a little bit more precise what the problem is with these arguments from beauty. It's not that per se that physicists like to talk about beauty, because as you say, experimentalists talk about beauty, and I don't think that's necessarily a problem. It becomes a problem if a large community has a very narrow sense of beauty, and that becomes an entrenched methodology that they are not willing to give up on, even though it's clearly not working. So I have no problem with people who value beauty in mathematics or in their work in general. It becomes a problem if it's a dogmatic a trend in the community. And maybe I should add there that I guess a lot of theoretical physicists would be insulted that I talk about beauty and accuse them of using notions of beauty, because they, by and large, don't understand what they are doing. So I was in a debate just on the weekend with Jim Baggett, and he says he prefers to call it metaphysical commitment. And that's entirely right. That's what it is. It's a metaphysical commitment. They have certain ideas of how their theories are supposed to look like that are not themselves scientific, but they use them nevertheless. Now, why don't I call it metaphysical commitment? Because you can't put that on the cover of a book, basically. So this is why I talk about beauty. I also think that historically, it's actually where it came from. It was this sense of beauty that people like to talk about. But now they're using notions of beauty like this idea of technical naturalness that you have in high energy physics that are just mathematical criteria, and they don't understand that these are actually metaphysical commitments.
And you talk a little bit about the book, and in the book about this most famous or kind of exponent of beauty, which is none other than the Nobel Prize winner. I can't decide if you use the word Nobel Prize more in your book or I use mine in my book. In fact, at one point you make an offhand comment about Brian Greene, and you put in parentheses, he has not yet won a Nobel Prize. So I thought that was pretty funny. But mention a character who's familiar to all physicists and is sort of the paragon for maybe the anti-Sabine school of thought, which is, physicist Paul Dirac, who basically said things tantamount to, that it's more important that your equations are beautiful than that they're correct. And I can't think of anything more anathema to an experimentalist than such a statement. But it brings up this notion of what is correct mean. And what I wanted to get your, and you've talked about this, and I should mention for the listeners, Sabine runs a phenomenal project, which is to explain some of the most complicated concepts in all of physics and astronomy on her YouTube channel. So we'll have a link to your YouTube channel, and also on your blog, which is renowned around the world, the Back Reaction blog, and that can also be located in the show notes that I'll include. But so Dirac casts a very long shadow. As I said before we started recording, I had on Eric Weinstein a couple of weeks ago, and he really, does seem to hold this high regard for the equations, and almost considering the incrementalism that has taken over physics since the times of the Diracs and the Feynmans, as kind of the tailor who puts on the last button, but is building on the superstructure that hasn't changed in 50 to 70 years, depending on what you're calculating, what you're discussing. But I wonder, do you think that physicists, as sort of looking at us as a sociological study group, do you think that we're driven by these kind of cults of personality, that we either follow Witten, or we follow Kamran Vafa, or we follow Stavros Dimopoulos? Do you feel like there's too much of it? Because I don't think it's the case in experiment. Again, in experiment, you might have a school of thinking, but there's so many thousands of people that are needed for billion-dollar-plus experiments that there's really no one person who can dictate the taste of a field, for decades to come, at least until after he or she wins a Nobel Prize. And sometimes it happens, but usually they're in their 80s. So what do you make about that? Is there a bifurcation in the culture of physics between theorists who might have this guru kind of mentality versus experiment? So maybe you just speak to, is that something that you've observed in your many travels?
Well, I didn't talk to experimentalists, so really I can't tell. I can only tell you what's with the theorists, right? And even in that case, I can't, promise that I'm giving you a representative sample. It's just a sample of people that I happen to have spoken to. Look, these are all really smart people, right? So to some level, I don't think it can get too bad. I mean, they do a significant amount of self-reflection, and I don't think that anyone would just dumbly repeat what Dirac has been saying and take this to be like the word of the master, and that's what I'm going to do. That's not how it works.
Right.
But certainly, I mean, what you see a lot, I think, in among theoreticians is that they, by and large, still believe in this idea of the lone genius. I'm going to sit here and think really, really hard about how nature works, and it will come to me, and everyone will understand that, I figured it all out, and I will be famous and get a Nobel Prize, basically. So that's where many of these people seem to be coming from. And I blame a lot of popular science books for that, which have propagated this myth of, there's this genius, may that be Einstein or Dirac or Feynman or who have you, who basically figured out how nature works just because they were so super smart, leaving aside that they were embedded in this large community of people who they could exchange their ideas with. And so you have now this community of theoreticians who believe that that's how their research is supposed to work, who completely ignore that they too are part of this community. And this creates a lot of problems, I think. And as you point out, in experiment, I think people are more used to being dependent on other people. You have these huge communities and everyone's doing their part, and really the magic comes from everyone working together on something. So you just have fewer people who are, insistent on on going it alone. Though one shouldn't, over exaggerate this. I mean, there are also of course, in theory, you also have people working together, right? Everyone's working together with someone. I just mean to say you don't get these huge collaborations.
Right. And when you look at science, so one thing that came up, is many times I've had on Stephen Wolfram and Eric Weinstein, Stefan Alexander, Jen Levin, and frequently I've discussed with them and Sylvester, Jim Gates as well, talking about this notion that, at least in my opinion, physicists have a certain amount of math envy naturally. And I think in theory, it's obvious it comes up a lot more, but in that, at least mathematics, the limits of what cannot be proven, or at least that certain things cannot be proven if mathematics is complete by virtue of Gödel's incompleteness theorem. But there is no equivalent for physics, for physical laws, physical quantities, parameters, what have you. And I feel like physicists use as a proxy the Karl Popper's demarcation hypothesis, which really was never intended to be the arbiter of what is good science, what is correct. He was really making a distinction between astrology and astronomy. I mean, he, for one, viewed the steady state model as much more compelling based on parsimony and Occam's razor type arguments. But nevertheless, I think physicists have this, desire to want to say that Popper is the be-all, end-all arbiter. And you talk a lot in the book about how, running through the themes of your own personal travels are the travels of the travails of the field, where you're just diphoton excess and everyone gets excited. There's 500 papers that come out about it. And then it just goes away. And I'm wondering if is this a byproduct of the stagnation of progress, in your opinion, that, there's so few and far between discoveries, and discoveries take so much time and money to make in the experimental field, that now we just have popularizers of science that can hype it up maybe beyond the level that it's warranted.
So you brought up a lot of points there.
Sorry.
Maybe let me start with a brief remark about the math envy. So I don't fully understand your remark about Gödel, because needless to say, a theorem is a theorem. So it applies, of course, to the mathematics that we use in physics. Right. So, but
Sure.
What the difference is that in physics, we're never quite sure that the mathematics that we are using is actually ultimately the right one. So you can always ask, like, maybe there's a better piece of math that would not, be affected by this no-go theorem. Mm-hmm. And there are certainly lots of no-go theorems for mm-hmm. one thing or the other thing. And I do think that these theorems are enormously useful. They tell you what you can and cannot do within the context of a given theory. So I think math is awesome, basically.
Soundbite: theoretical physicist claims math is awesome.
Maybe I should add that. So I originally studied math.
Mm-hmm. And then, okay, so mathematical physicist.
I fell off faith and became a physicist.
I guess I just mean that I hear a lot, that, this is not falsifiable. Therefore, I mean, nobody's disputing the unreasonable effectiveness of mathematics and physics, to use Wigner's term, right? But how is it possible that an experimental physicist, for example, you have this discussion with Garrett Lisi, who's a UCSD alum, and he's basically saying, like, well, you can't prove that you can't prove this about, and so it's untestable, and you kind of badger him a little bit in a friendly way. Well, I bet the masses of your particles are just well beyond the horizon of detectability. But what if there was? I mean, people say, just to cut it. Hi, Sabine. Sorry, me.
There you are.
Yeah,
yes.
Sorry, I got kicked off for some reason, but it should be better. So I was asking, you've no doubtedly heard that people will say, well, string theory is not really.
So the audio is not.
It's good. Yeah. Hold on.
The audio is not good.
Let me try one more thing. Hold on. Edit this out. Okay, is that better? Is that any better?
So I hear you at least, so that's better
Okay.
than not hearing you, I
Okay.
guess.
Yeah, let me see one last thing. I have a hardwire connection and a Wi-Fi connection. Maybe they're battling each other, and that's the problem. Okay, this should be better. Is this better?
Well, say something.
Can you hear me now with my...
Yes, I hear you.
Okay,
Yes.
good. Okay, so this should work better. So I was asking.
I let me tell you where I lost you. You said something about unreasonable. No one doubts the unreasonable effectiveness, and then.
Oh yeah, so the famous what is it, Wigner's statement that what's so unusual is how unreasonable mathematics is in physics, and nobody's doubting that math is used for various purposes in physics. But the problem is, how do you determine if a theory like string theory or the multiverse, et cetera, paradigms, if they, if, as it's often stated, not directly by you, I don't think, but that it can't be falsified. So let's not, I mean, it's often used as a way to dismiss something by critics of string theory. Oh, it can't be tested, it can't be falsified, so therefore it's not science. As if Popper is the ultimate arbiter of what's right and wrong, the way that Gödel is the arbiter of what can be provable or not within the context of mathematics. Does that make sense? Popper, reliance on Popper.
But there are many things to be said about this. One thing is that Popper didn't use falsification as the one and only way to tell science from pseudoscience. So that's just rubbish. Actually, I think that this is part of the problem that you see in high energy phenomenology and in other related areas, is that they tend to think that just because they are able to make a potentially falsifiable prediction, it's science, which is nonsense, of course. They use this to excuse a lot of mathematics, basically, and hide all their guesswork in some kind of equation. But that's, in the end, that's exactly what it is. It's some guesswork. And so you were talking about this diphoton anomaly that disappeared. So I tell this story in my book, where they had these 600 papers that were published within a matter of a month. And this highlights exactly this problem. They believe that this is good science, largely because, that they are making some kind of prediction, basically. So maybe that's not the best example now that I think about it, because it wasn't even a prediction, it was a post-diction.
It's a retrodiction, right?
Yeah.
Post-diction.
So not even that in this case. If you look at the phenomenological models that people are using, like for supersymmetry, you have all these supersymmetric, these variations of supersymmetry that supposedly tell you what's the mass of this or that particle, all the dark matter models and so on. That's all supposedly science because they make some kind of prediction. And so I think this is just wrong. This, of course, also means that you can't just go and dismiss string theory because it's supposedly non-falsifiable. So I should add here that this isn't even true. String theory is in principle falsifiable. I mean, it predicts that the world's made of strings. I mean, that's a prediction. The problem is that it's unfalsifiable in practice. No one's going to see these things in the next 1,000 years or something. So really, that's not the problem with string theory or multiverses and so on. But really, the problem is that these theories are just unnecessary to begin with. They don't actually solve any problem. They don't constitute any kind of progress. And so this brings up the question again, then why do theorists work on this stuff nevertheless? Right. And that's because they think it's prettier. So you put up this image about supersymmetry.
Behind me.
You can ask, well, why do they believe in that? Well, because they think it would be pretty if there was some kind of symmetry relating the fermions and the bosons.
And there are symmetries that relate, octets, and I mean, symmetry has played a huge role in construction of what's known as a standard model. So it's not without justification that, I mean, it shouldn't be your starting point. And I guess your point is that too many people say, well, let's look for something that's incredibly beautiful. But that might be just a mental shortcut, a hack, to get to the answer faster, perhaps.
Well, you shouldn't lose the problem that you're trying to solve out of sight. So you're right, of course. Symmetries have been very useful in physics. So it made sense after the standard model was largely completed to try to increase the symmetry and see if that works. And that's exactly what people did in the 1980s. But the thing is, it did not work.
Yeah.
They tried these grand unified theories one after the other, and they were ruled out one after the other. They've been looking for supersymmetry also since the 1980s, and basically was ruled out in the 1990s. It's just that they didn't give up on it. Instead, they fixed the theory so it was still in agreement with data, and then it was supposed to be found at the Tevatron and at LAP, and then it was to be found at the LHC. And each time this didn't happen, they came up with some excuse. And so that really is the problem, that they're not learning from their mistakes. And that's really, the most important thing in science is that you learn from the data you get. And exactly that's not happening. And that's really the problem.
So when you wrote an article, an op-ed for the New York Times about a year or so ago, and it generated a tremendous amount of heat and even some ad hominem attacks, which you don't need me to defend you, but I do take offense at people in my field. Usually they're men that are, perhaps there's some level of insecurity when they see someone as successful at communicating ideas as you. But there were some legitimate complaints that I heard from my colleagues that I took as legitimate, and I'm going to take the opportunity to just level them at you, crush you. No, I'm not going to do that. But you're impervious anyway. But one of the arguments was, that you're making is that, we should be careful building this future linear collider. So there's a picture of it, an artist impression behind me, and it just engulfs the LHC. And part of what you were saying is certainly legitimate, that, of course you can always say we just need a little bit more energy, we need a little bit more money, we need a little bit more time, but these are all finite resources. On the other hand, we in the USA learned a very painful lesson in 1993. I was a beginning graduate student, and I remember the moping faces in the high energy physics department, part of the physics department at Brown University, just devastated by the cancellation of the superconducting supercollider. And for about a millisecond, I didn't understand it. I said, well, they'll just use the money for something cool, besides that. They'll build some other, a giant telescope. But that never happens. And in fact, that was very naive of me to suspect that. So where do you really come off in this conversation? Because what you say carries a lot of weight. People listen to you, and I think your voice is extremely important. When you say, like, we shouldn't build something like this, you're really saying, like, physics doesn't need funding, or perhaps the physics shouldn't receive this funding. So my question, I guess, is to you, given that money is not going to be used for physics, do you think that we really shouldn't argue for making advances, even if they're incremental? Do you think that runs a risk of maybe damaging, progress in physics, albeit it might be less, quantum leaps than we would like?
Okay, so a few things. One thing is that you said the future linear collider. It's
circular. I have FCC and
I was like, wait, what's he talking about?
Oh, there is one, ILC, right? There's a Chinese one, at least NEMA.
Right. But I think the one that's behind you, it's definitely not linear.
Yeah, right.
So, now about this argument with the superconducting supercollider, this is like one of the most common complaints that I get, and it's just rubbish. So for everyone who's interested, I have on my blog a list with the most common nonsense arguments for building a bigger collider, and that's like, I think it's number 1 or 2. And so this argument that, like, if we don't build this larger collider, it is not necessarily going to be used in the foundations of physics. That's of course correct. It may be. I just don't know. That's a political question, and it's not a question for me to answer. The question that I'm answering is this a good investment? And the conclusion that I come to is no. And that's all I have to say about this. And so now you can ask me, like, are there other experiments in the foundations of physics that would be good investments? And in these cases, there are some cases where I would say, yes, most likely. I can't be sure, but at least the expected return on investment is not as terribly bad as it is for this bigger collider. And if you look at the societal context, it's an incredibly difficult question to answer, where I just can't make any, sweeping statements, especially now with the economic situation looking so difficult. I just think it's irresponsible, to say, well, please give us $40 billion to build this larger thing, and we can't tell you really what's going to come out of it, but you will make a lot of particle physicists happy. I'm sorry, do you really expect me to sign this?
Well, I guess the question is, a lot of things in physics that have led to great breakthroughs, and I've written about this, are serendipitous. And, the hardest thing in life is planning on serendipity to save you from an experiment. But I guess that, the counter argument would be, well, there are aspects of building an apparatus that just scale with energy, or energy to some power. And yes, there's, if you know there's a no-go theorem, so to speak, if you know that there's a forbidden region of energy space, of parameter space, of cross section, et cetera, then yes, then I would say, looking for something that's forbidden and is demonstrably so, that is a waste of time, and we're not good stewards of taxpayer money. I guess, there is the other, and this is an image from your website, just when you talk about the CERN, marketing video, as you call it. And there is a strong sociology, because I think, in Eric Weinstein's words, that we're sort of really fighting over these crumbs of the last great revolution. And I wonder, when you think about it, I don't know if you've ever heard of this book or theory. It's called The Fourth Turning. Have you ever heard of this? It's this guy Neil Howe and another guy, I think Strauss. They write about these paradigm shifts in society, where you go basically centered around wars or famines or revolutions that lead to different periods of social upheaval and then recovery. And I wonder, he characterizes a period of war, as obviously maximal upheaval, but offering in the recovery phase, like the baby boomer phase, so to speak, a chance for great wealth and prosperity. And I wonder, do you see any parallels with physics in that, we had a tremendous number of breakthroughs in the 20th century, and maybe by some estimates, we're still making tremendous progress, even in the foundations of physics. One of my readers sent me a list of like 8 different huge breakthroughs in his opinion, ranging from things like Jim Peebles' work on perturbation theory in the cosmos to quantum teleportation. These are big breakthroughs in fundamental aspects of physics. But nevertheless, do you think we might just be in a lull between these different seasons of the society of physics, the culture of physics, where we're on the precipice of a great breakthrough?
Well, so I don't know this societal theory that you just talked about, but it sounds very similar to Kuhn's model of scientific revolution, right? So you have these upheavals, and then you have some period of normal science where everything flourishes and so on. So if you're asking, like, do we need the next revolution? The answer is basically yes. So you're noting that there are still things happening in the foundations of physics. It's not that people are just sitting around twiddling their thumbs. That's certainly correct. Just because you do normal science doesn't mean you do no science. But the thing is that we have these big problems in the foundations of physics that have remained unsolved for more than 80 years. Basically, if you think of something like dark matter, or what's the quantization of gravity, what's with the interpretation of quantum mechanics, right? So these are not new questions, and there has been zero progress on that, nothing. And that doesn't mean that there are no other things that people have done, as you point out. Certainly there have been other things. So yeah, I'm not sure if this answers your question. So
yeah, I think it does. I mean, the main thing is that there is a cycle where you have the public who has a vested interest, and fiduciary, responsible people taking care of their money, their stewardship of their finances. They also have an interest in the results of the science, as much as, we scientists are not great at exposing, what really fascinating work we're working on. And then there's this, kind of hype, mini cycle where, you have your university press office, and you've got your local newspapers, et cetera, that want to build up the research that's going on. And I just wonder, in an era, since we're experiencing now this great, potentially this great recession or whatever, might even be worse, in this era of a declining, budget dollars, where do you think people should spend their time? In other words, it's not for lack of brain power. I can point to 20 people working on dark matter and dark energy. What do you think it will really be that leads to, the most bang for the buck or return on investment, given that we live in a constrained resource environment? In other words, why shouldn't we spend money on COVID research and CRISPR and devote that to dark matter, discovering aspects of dark matter?
Yes, that's exactly the right question to ask. So maybe let me briefly return to something you said earlier. You were talking about the serendipity that led to many breakthroughs. This is another one of the nonsense arguments on my list, because you can make this argument about any experiment. Right? Any experiment that tests something that has previously been untested. You can say, well, we could just be lucky and find something. So what you should do in this situation, you should choose that investment that is most likely to give you the biggest bang for the least amount of bucks, basically. And this bigger collider just fares very, very badly because it's a lot of buck and very, very unlikely to do any bang. And so what you're saying is exactly the right question to ask. Like, where are you most likely to make some breakthrough? Now, you say something about COVID research and so on. Again, if you want me to make any statements about societal relevance, I think I'm really not qualified to do that. That's a very involved question. I would just vaguely say that whenever you are thinking about science investment, you have to think in very, very different timescales. There is research that is going to be important right now, like this COVID stuff. Then there's research that's going to be important in the next 10, 20 years, like say anything about genetic therapies, what have you. And then there's research that's going to be important in 200-300 years or something. And that's where you can put high energy particle physics or foundations of quantum mechanics and that kind of stuff. And so to have some kind of balanced budget, you should cover all of that in a certain division. So that's the difficult part to work out, and I'll leave that to an economist. So that's for what the overall societal problem is concerned, and I'll leave it at that. So now, if you look at the foundations of physics specifically, I feel much more qualified to say something. Because what I've basically presented in my book is an answer to exactly this question, like what are the areas that you should be focusing on where you are most likely to make progress. And the way that I present this argument is by looking at the history of physics. Like you can ask, if you look at the history, where has progress come from? And so, yes, there has been experimental progress, of course. So there were these discoveries of serendipity. This is a terrible word. But so the problem with those is that new experiments are getting more and more expensive, and it takes a longer time to build them. So just poking in the dark by building experiments, that's not an option anymore. But we're way past the stage. And this puts a heavy burden on theorists because they have to come up with arguments for what's the next experiment that we should be doing. And so that's why theorists have to be really, really careful with what argumentation they rely on. And now this brings us to the other type of breakthroughs that we have seen in the foundations of physics, which were those that were led by theoretical predictions. And now it's very interesting, if you look at the cases where this has actually happened, it was always by solving an inconsistency in the existing theories. And by this, I mean just a mathematical disagreement. If you think about, for example, Einstein's special relativity and also general relativity, the former was an inconsistency between the Galilean invariance and Maxwell's equations. It's just the wrong invariance. And then once you have special relativity, you notice, well, that's actually incompatible with Newtonian gravity. So you have created another inconsistency that requires a solution that brings you to general relativity. And then once you have special relativity, you also notice that this didn't fit together with the original formulation of quantum mechanics. And resolving this inconsistency, that's what Dirac did. And so, yes, Dirac was talking a lot about the beauty of his solution, but he also had a really, really good problem to solve in the first place. And so this is, I think, the reason why these mathematical breakthroughs worked, because they had these inconsistencies. And there are other examples. For example, the Higgs solves an actual inconsistency. Now, if you look at all the failed predictions in the past 40 years, these were not theoretical predictions that were based on solving an inconsistency. They were based on wanting to make the theory more beautiful. And so the answer that I come to towards the end of the book is focus on solving real inconsistencies. If you want to make theoretical progress, that's what you should be doing. And so this returns us to this issue with the question, should we build a larger collider? In this energy range that the next larger collider could be testing, there are no inconsistencies that require a solution. And that's a situation which is entirely different to the situation for the Large Hadron Collider, where you knew you have these unitarity problems that required a solution. That was an actual inconsistency. So we knew that something had to happen. Not necessarily the Higgs, but there had to be some solution to that. So we knew that we would see something new. And yeah, well, the Higgs it was. But for the next bigger collider, there just isn't anything remotely like that. The next inconsistency in the standard model is somewhere where the issue with the neutrino masses becomes relevant. And that's not until, I forget, 10 to the 13 GeV or something like that. So it's way, way off. You're not going to get there. So you should be focusing then on more promising inconsistencies. Something that's closer around the corner. Dark matter is like the obvious candidate to name, right? Because in that case, okay, so this is not a theoretical internal inconsistency, but it's an inconsistency between the theories and observations. And in this case, at least, we do have observations. So we have something to build on. And then there are other inconsistencies, like the missing quantization of gravity is an actual inconsistency. It doesn't fit together with the standard model. There's the measurement problem in quantum mechanics. And there are other mathematical problems in quantum field theory themselves. And now the problem is, this returns me to what I said in the very beginning. Solving these problems is really, really, really hard. And so people are not going to do it on a short-term grant if they have to produce results quickly. What they will be doing instead is that they will do the easier stuff, and that's producing these piecemeal, little tiny incremental things that you can publish and you can put on your CV, and then you will get a job.
So speaking of that, we both have to get back to our respective jobs. I had about 20 more questions to ask you. Maybe we'll do a part 2 over the summer, because I do want to talk about big astronomy projects, which also suffer from potentially their own success, being victims of their own success in the past, and and just making it so expensive to build. This project CMB stage 4 experiment, the experiment I'm involved with, called the Simons Observatory, is a $100 million class project. CMB stage 4 could be more. And as usual, we only quote
that's all peanuts compared
I know,
to the collider.
Well, but remember, when you quote an experiment, it's always it's only just the capital cost, not the operating expenses. So you should double all the costs you see from it. And whenever you see an experimentalist give you a number, always double it. But the last question I do want to ask you in the last couple of minutes you've had a remarkable career. You've done many different things and have acted as a role model for physicists in all different disciplines and young people in particular. I wonder, based on the name of our podcast, which is the Into the Impossible podcast, that derives from Arthur C. Clarke's law that the only way to find out what is possible is to venture a bit beyond into the impossible. I always like to ask my guests, what fact of life or what aspect of your life made no sense or seemed impossible when you were in your 20s, perhaps, and now makes perfect sense because you ventured into the impossible, so to speak. So advice to your former self.
Oh my God. Let me maybe say one thing though. You speak of my great career. Let me point out that I don't have a permanent position. Yes. I sit on short-term money. So I'm working on some project and the funding on that will run out in 3 years and then God knows what. So much about my great career.
So buy more books, buy every single copy. I've got all 3 different versions.
Yeah, I mean, so what didn't make sense to me so I've always had a very strong interest in philosophy that I always, as a physicist, felt was somewhat of a waste of time because, you know, scientists tend to be very dismissive, you know, of your philosophical interests. And now I'm glad I paid some attention to it because it turned out to be much more important to my research than I had ever anticipated.
Well, that's fascinating. Thank you, Sabine. So where can people find you online and when can they expect your next book after this one?
So how do you find me online? You know, my name is not very common. You Google my name and I'm like the first 100 hits and I'm on YouTube and I'm on Blogger and I'm on Facebook and I'm on Twitter. I'm everywhere.
Yeah, we'll give folks links. What are you working?
It's not difficult.
And then what are you working on in terms of a future book? I heard rumors that you might be working on.
Rumors. Oh, yeah. Yeah, I'm supposed to be writing a book, but you know, COVID got in the way, so it's not moving a lot. But yeah, so I have a deadline next summer, and it will be about physics again.
Oh, great.
That's not so hard to guess, and it's about all those deep philosophical questions that your physics professor told you not to ask.
Wonderful. I can't wait to read it. I'm sure it'll be another bestseller like Lost in Math, which comes out now. By the time you're listening to this video or an audio, it'll be out in bookstores in America. And I just want to thank you, Sabine, for sharing your time, your ideas, and again, as an inspiration to many young people because of your the rare quality, one of the rarest qualities of all is your courage. And I do look up to that. And I thank you for sharing your ideas and most importantly, sharing that vanishing quantity called time. So now I'll release you back into the woods and enjoy the rest of your evening there in Germany.
Thank you for the lovely conversation.
Bye, Sabine.